I'd like. Oh. Okay. Recording in progress. Okay. I'm just going to move right along here. Got it. Okay. All right. So, of course, I'd like to thank Southwest Florida Coders for inviting me, and Zarella and Crystal. They're great. If we give them a bigger hand. Okay. And there's some Python involved in tonight's talk, so I put the Python up there. I was also a member of Southwest Florida Tech. It used to be Southwest Florida Regional Technology Partnership. They actually got me involved with Raspberry Pi through a grant that they got from Gannett. I worked with a colleague to develop a little program where we gave away a bunch of Raspberry Pis, and we had a lot of fun doing that. I'm also a volunteer for FIRST. If you've ever heard of FIRST, you can go to firstinspires.com or .org. They basically inspire young people to pursue careers in STEM, science, technology, engineering, mathematics, and they do that by hosting robot competitions. So for grade school and middle school, they have First Lego League. At middle school, they have First Tech Challenge. In high school, First Tech Challenge. And then for high school, they have First Robotics Competition. So if you have kids or no one has kids and they're interested in science and technology, check out firstinspires.org. There's teams in this area, and some of them, like Java the Hutts, are actually championship teams. Pretty good. Okay, so the Internet of Things, discussion on building local network devices. So as I said, building a local network device, this is the project, is the MacGuffin, as they'd say in the movies. The project really isn't what's important here. We're going to be talking about how these things are supposed to connect together and how we can develop these things. So the title of the talk tonight was Intranet of Things. You've probably all heard the word Internet of Things, which is kind of like the more popular cousin to Internet of Things. If you do a Google search, you'll find a few results for Intranet of Things, but not too many. So if you think about what the Internet of Things is, we've got all these different devices. So you've got some device that does something in your house or in your office, and it connects to the internet. It goes to a router, and then from the router it goes out to the internet. It goes to a cloud computer somewhere 1,000 miles away, makes a little decision, sends back a response back to your router, back to the same network that it just came from, and out to some other device that's probably only a few feet away from the first device. So the question is, does this make sense? I don't think so. I think there's a lot of reasons why, if you're already on the same network, you should just talk to the device on the same network. And the use case for that is probably an order of magnitude greater than the use case for connecting to the internet. Now, certainly, if you think of something like a light bulb, there is a use case that says your light bulb on your front porch might be nice. If you're on vacation, you could turn on a front porch and think, people think you're home. But for most of the light bulbs in your house, the time you're going to use them, you're going to be in the house. It doesn't really matter. So light bulbs don't need to connect to the internet. Maybe they need to connect to a hub someplace, but they need to connect to your phone if that's the device that's controlling them. But you're going to be there. So that's really an Intranet of Things device. So what I'm really talking about is something, a LAN first approach, local area network first. So if you're thinking about, I want to build an Internet of Things device, think about what is this device going to do? Do I really need to think about how it's going to connect to other devices locally, and not so much about how it's going to talk to the internet? And so the LAN first approach would be things like, does it do locally useful work? So if you think about a video camera in your living room, okay, that's monitoring your living room. It is working locally, but if you're in your living room, you're not really going to be using that. It's not useful to you locally. It's useful to you if you're at work, or it's useful to a service or something. A refrigerator might have some IoT device embedded in it that does maintenance. So it's going to say this device is functioning correctly. Well, that's not useful to you locally. That's an Internet of Things device. So is it controlled locally? You control it from your phone. Is it useful to other local devices? So an example might be a thermostat. So a thermostat is really only for your air conditioner. You might want to have some kind of historical log or something, but your air conditioner is almost always going to be local. So that's kind of a Internet of Things device. And if you think about it, that's not the only thing you can do with a thermostat or just any kind of temperature sensor. You can have a third-party program can listen to that temperature sensor and say that this sensor is increasing in this room, but not some other room, and maybe it has a way to zone the AC different from what the default would be. Or it could actually say, hey, let's just raise some shades instead of, or lower some shades instead of turning on the air conditioner. So different devices can use that sensor for different things. And the last point here is, are there multiple installations to coordinate? So like, again, back to the light bulb. There's not just one light bulb in your house, there's a bunch of them. And you might be changing the color, you might be changing the brightness. So these are really good Internet of Thing kind of devices. And once you think about Internet of Thing device versus Internet of Things, you start thinking about, how do I connect these devices locally and not using a service? You imagine the problem if you had all your lights in your house required the internet access to turn them on, right? You might find yourself sitting in the dark some night. Or maybe the default is for all the lights to be on fully. So it's like you're standing on the sun in your living room. It's just not a good use case. So this is kind of what I think the market is like. You could take my word, you could look at this graph, but or the chart, but I made up the chart, so it's just as accurate. According to data that I got from Statista.com. See if I can. I don't know if you guys can see this over here. Uh, 68 million annual PCs are sold annually in the US. 68 million. 74 million smartphones, tablets, and stuff are sold. So those are pretty big markets. But if you think about the market for IoT, and this is why everyone's so excited about it, it's double that, right? Because it's not just the computer, it's not just the cell phones, it's every appliance, right? It's every camera. And if you think about the market for Intranet of Things, those things that don't really need the internet, I think it's double all of those combined, because it's every light bulb, right? It's every sensor. It's all the things that you don't even think about, because they don't have to connect to the internet, but they're just nice to have, nice, useful things. One of the ideas I tell people about is, if you have a light bulb in your living room and you have a proximity sensor, right? So that's one device. And the proximity sensor tells some program that there's people in the living room. And then the same program says, hey, we just finished making coffee in the kitchen. So I'll flash the lights in the living room to tell them that the coffee is done, right? So this is how Internet of Things devices can work together in ways that Internet of Things devices, kind of struggle with. Now there's a number of different ways to do this. There's protocols, frameworks, and APIs that are involved. And I'm just going to touch on these briefly. We're going to actually do something that would be using Wi-Fi, and be doing that experiment tonight. But Wi-Fi and Bluetooth are some that you're familiar with as far as protocols for how you exchange this information. Zigbee is maybe one that you're not familiar with. It's kind of a low power a version of Wi-Fi. It creates a mesh network that connects all of your devices, so that if you have one device in one room, it's got a very poor signal, but it can connect to some other device in another room. They can all mesh together, so you have very good coverage throughout your house. This is actually becoming a very popular standard. MQTT and CoAP are also protocols. The MQTT is message queue T something transport. And it basically leverages all the TCP/IP infrastructure to do IoT stuff for small micro devices. Then you get down to some of the frameworks, and I've got these kind of listed. As you would expect, all the big names: Cisco, Salesforce, Oracle, right, Microsoft, and of course AWS. Embed is, I've got that underlined here because Embed is actually really interesting. It's being put out by ARM. I think it's under the Apache license, so it's very free. You can do things with it, and it's, of course, it works with the ARM architecture, which is in the Raspberry Pi. And of course, then there's Matter, right? So what's the matter with Matter? Matter is the big industry initiative. There's over 250 really large technology and manufacturing companies, electronics manufacturing companies involved in Matter. It's kind of a club. They're developing APIs, and if you're writing an application, you want to connect to stuff that's off the shelf, Matter's a good thing to look at. You want to connect to Google or Amazon to their stuff, Matter's a good way to look at it. The problem with Matter is these are APIs that are developed for specific products, and if you're not in the club, your API is not going to be part of that conversation. And if you're wanting to do original things, if you're trying to do something that's not off the shelf, you're going to find that other people aren't going to really be able to use it through this platform, or you might have a difficult time selling into this platform. So what's the alternative? How do we, if you're a maker, you're a software developer, you want to do something special, you don't want a lot of hassle, you don't want licensing, you don't want to have an internet connection. You can use your Raspberry Pi. I'm jumping ahead on my screen, excuse me. Let me back up. The answer is sockets. Sockets are a low-level programming tool that have been around since the beginning of the internet. I think they came in around the 84 is when the first internet protocols and things started getting locked down. Now, how many people here are familiar with sockets networking? So about roughly a third to half. Okay, so I'll cover it briefly. It's not really a tutorial on sockets, but sockets are how machines communicate on a network. You all use IP addresses, and most of you understand what the port is. Your port 8080 or port 80 for your internet, or is it 444 for SSL and or yes. These are all sockets. So what happens is when your computer wants to connect to another computer, it sends out a signal to a router. It says, I want to find this computer with this host address, and that router then says, I know who that computer belongs to. It has a list of what are called MAC addresses in its table, and it knows exactly where that computer is, and it sends out that message, and it looks at the port, and it says, okay, I'm going to connect to, when it gets to that computer says, okay, you found me, who do I give this message to? And it looks at the port, and the port is the application that's running on that computer. So if you want to run your web server, it's going to be usually running on port 80. If you want to run your FTP server, I think it's port 29. And of course, there are a lot of ports. It goes up to, well, 56,000, almost 56,000. Anyway, there's variations on that, 65,000 percent. So the socket API is found in most programming languages. You won't find it in JavaScript because it's hidden. It's one of those things JavaScript kind of wants to sandbox you away from. It does let you use fetch, and it has some other APIs like web sockets, which are not actually sockets. Those are protocols, and they wrap around sockets. But Python actually has a socket API that you can actually use, and that's what I'm going to be showing you tonight, is some code that uses Python sockets. You can also use sockets in Java, and you know there's socket APIs in a lot of programs. And what the socket does is it allows you to connect your program to another machine. So if you imagine you have two either Raspberry Pis or two IoT devices, you want one device to talk to the other one, you have to open a socket. And then once you open that socket, you can send messages through. I'm going to go back. See. I'm not going to really cover Raspberry Pi in depth, but to give you an idea, these are some of the devices that are out there that you can experiment with. The Raspberry Pi 4 Model B is one I've got here. The 4 Model B is just a form factor. There's also a Model A, which is slightly larger. If you see down there, there's a Raspberry Pi Zero, and on the upper end, you have things like Latte Panda and Intel NUC, which are x86 processors. They run Windows. They're much more expensive, but there's literally dozens and dozens of these single board computers. And there's also microcontrollers like our Arduino, Raspberry Pi Pico, which we actually have one down here. We'll show it later. And Arduino, the Uno. These are microcontrollers, and they're a little bit different from your Raspberry Pi. They don't run operating systems. The Arduino actually has its own programming language. It's similar to C. All of these, however, do run a version of Python called MicroPython. It's limited, as the microcontrollers are. They tend not to have a lot of threads. Sometimes they just have one thread that just loops. Okay, so the kind of sockets that we can use for working with our Raspberry Pis and our microcontrollers are part of the Internet Protocol suite of applications. Some of these you're familiar with. TCP, right? You hear TCP/IP, the Transfer Control Protocol. That's the one that made the internet happen, really. Then there's another one called UDP, and people aren't as familiar with that. UDP is really interesting because it's not very reliable. It doesn't send a lot of data, but it sends it to everybody. So if you have a message that you want everyone to hear, you can use UDP. The thing that I was trying to get to work earlier, not having success with, was connecting the UDP to the network, and I'm pretty sure that the administrator here has a different idea of what IP addresses I can use for that than what I've got at home. So it didn't quite work. Now, the reason that's important is how you want to connect these things. So if you think about this, this is a basic kind of service when you know what the other device's IP address is. So, and if you look, it also looks kind of like a web service too. You have an IP or IoT service, and it knows what the address is. So it sends that a request to its TCP client, and then the TCP client opens a socket. It sends it to the TCP server, which then reads it and then sends that back out to the IoT device that processes it, and then maybe sends out a response. Okay, so that looks pretty familiar. But what we need to do is, if you've got a bunch of IoT devices that don't know the other one exists, how do they discover each other, right? And the way they discover each other is with UDP. So my IoT device, now there's different ways to do it. This is just one way. But my IoT device will basically says, I've turned myself on. I want everyone to know I exist. I send a message to my UDP server, and it sends out what's called a multicast datagram to the entire network, or the local network. It doesn't go out to the internet. Sends it to the local network. And then anyone listening with their UDP client will hear that message. Of course, the message I'm going to send is really simple. What's my name, right? What's my IP address? What port can you connect to? And then I might have some sort of security information, maybe either a hash code or something that you can verify that I'm part of your club. So that's going to go to the IoT service. It's going to validate that this is a device I want to connect to, and then it goes back through and does the original stuff. Connects to its client, sends a message to the TCP server, and so on. So the multicast datagram really only has to happen once, but it has to happen consistently. So the way I do it is, I will have, when the device first turns on, it's going to send that message a bunch of times because it doesn't know who's listening. So for maybe the first minute or so, and you'll see this on your modems, you see on your routers, you'll see this on your Roku or anything like that. The light's blinking. It's sending out its message, right? That's what it's doing. It's saying, I'm here, this is me. And anyone who wants to get that message can, and maybe do something with it. Then after about a minute or so, I'm going to figure that I want to get the message has got the message, and I'm going to stop using network resources and maybe only send that once a minute, which is why sometimes you lose a connection. You go, why isn't it picking it up right away? Because it's not really sending it out as much. So it does that. My client, it can either keep listening for other devices. My IoT service, like if my service is on the phone, or my service is the air conditioner, or whatever's listening to IoT devices, it could either keep listening or it could say, okay, I've got one, and shut down my UDP client. Doesn't matter. So that's kind of the Intranet of Things talk. Let's get into writing some code. Well, I'm not going to write some code, but I'll show you some code. I'll talk about this project, which it isn't quite working because mysteries unexplained. But I'll talk about what that project is, I guess, just to get it started. So I started thinking about, like, what kind of project would I do for an IoT talk? And I said, well, I could make it real simple. I could turn on a light, which would be kind of a pretty weak demonstration. So I thought, well, why don't I do something like a people counter? So you walk into a room, and it increments the number of people in the room. You walk out of the room, it de-increments the number of people in the room. Now, there's a couple of different approaches to doing this, solving this problem. One, of course, is to use cameras where you're monitoring people's faces, to use facial recognition. Very accurate, really creepy. Very possible, but very creepy. But there's a little libertarian spot in my heart that dies every time I think about pointing a camera at someone without their knowledge or permission. The other ideas are like passive approaches. One of the passive approaches, and let me jump out of the frame here for a second. Okay, so one of the passive approaches is to use a proximity sensor. And proximity sensors are actually pretty cheap. This one, I don't know if you can see it online. You guys can see it back there. It's pretty small. It has a little dome on it that is called a Fresnel lens that takes in infrared from all over the room, and it's particularly tuned to human beings, right? So it's really good at detecting animals and things like that. But if you take that part off, you've got a nice little cylinder, and if you put that cylinder in a little hole, see this block of wood, I don't know if you guys can see that. It kind of works like a beam. So it's not as good as a laser, but it's really passive. It's really cheap. I bought a bag of 7 of these for $10. Some people charge 15 a piece. Say who, but you can find them for pretty cheap. They're not perfect. They're not perfect. There's another solution that is maybe a little better. I should have had this opened up. This guy shows me. This is a range detector. And this range detector, it sends a signal to your Pi in voltage. So if you can figure out that if that voltage changes, somebody has passed in front of it, right? So I did not try that one, but the proximity sensor works pretty good. Now you have to have 2 of them. You have to have one for walking in and one for walking out. You just have one, you could have one guy that walks in and out 50 times and you get 100 people in your room on the counter, right? So it's not very good. All right, let's see if I can get some code showing here without messing this up. Well, that's okay. So I created this little piece of code for my GPIO switch and my what I call it transition counter. So you're transitioning between the inside of a room and outside of the room, and basically any device that would measure something going from where one device triggers and then another device triggers could be measuring a transition. So you might have 2 devices or 3 devices or whatever. I probably shouldn't go through this code too much, but if you're familiar with Raspberry Pi, there's a thing called a GPIO pin. That's what makes Raspberry Pi special. It allows you to do inputs and outputs that you don't have in your own computer, but you just have a little piece of software that can tell if a pin is high, meaning it's got a current going through it, or low, meaning it has nothing going through it. And what the proximity sensor does is it just says if somebody walks in front of it, it triggers, and you can just measure whether or not it's high or low. Let's see. basically when you use a GPIO pin, Raspberry Pi, you're using the RPi GPIO library, and you just want to set up the pin. Every pin has a number that you want to use, and you just set it up. I say I'm setting up my GPIO pin. I pass that pin number into my constructor here. So, and then I'm using a part of the API that allows me to detect changes in that high or low. So I'm detecting a change in the high or low, and then when there's a change, it sends it off to a trigger. And here's my trigger, and then it just runs through an algorithm. If it's been triggered high and the other one, if the outside one's been triggered and the inside one hasn't, then it's just going to assume that, okay, someone's walking in, the outside or the inside one's been triggered, the outside hasn't. If I said that right, somebody's walking out. And that's all that does. So it's pretty simple code. How do I get that code to a giant screen that would count how many people walked in? If you wanted to see on your wall how many people were in the room, or if a security person wanted to know how many people, if the room was over occupancy, or if I'm doing a speech and I just want to keep track of when people walk out, it'd be a good idea to use that device. Perfect Intranet of Things device, really. A lot of people can use it. It doesn't have to connect to the internet. So how do we implement a people counter? Because that's essentially what we want to do. And here I've got an application that I called People Counter, and my People Counter is going to have it launches a display on the screen here. You could launch a display on the Raspberry Pi. You could read it out any different way. It just needs to have a way to listen for the changes in the actual count, and it does that because it first gets the IP address from the UDP's client, or from the UDP server, it sends it, and then it polls. So polling is a pretty simple method. Just every couple minutes, it's gonna poll, and it's gonna ask, or every 2 seconds, it's gonna send a TCP request and says, has the number changed? Now that's one way to do it. On a local network, it's not that big of a deal. You've got a couple of devices running. If you were on a really big network and had thousands and thousands of people, it wouldn't be a very good idea to do that. In that case, you could have your socket set up for two-way conversation. You just don't close it. Typically, when you use a TCP/IP connection, you will close that socket as soon as you're done doing your business, because you don't want to tie it up. So polling works good in this situation. Let's see if we could look at what a server looks like, and then maybe we'll get to see how that server is turned on, how it connects. So I created a couple of modules here. Device module and a server module. Okay. If any of you are have problems with reading code or doing code, this is probably going to be very hard. And for some of you, this just might just be boring. So so bear with me. It's too bad. I'll try to keep up the pace and not get too into the weeds. First thing I did in Python is I created an IP socket address object. And the reason I did that, I'm just going to get back here, is because there isn't one. They have a way to get your IP address, and they put it in a tuple. Anybody familiar with a tuple? So you've got the IP address and you've got the port and a tuple. I kind of wanted to do a little bit more. I like things being packaged a little better. So I just created my own class for IP socket address. And it can give me my host name. It'll give me the tuple here. It'll tell me what family. By family, you got IP4, IP6. And then it has a couple of useful methods. One is opening the socket for me. And so then I want to create a TCP server. So the job of this is to listen for people who are doing requests and to send responses. And anytime it gets a request, it's going to forward that back to the device. That's the IoT device. So it creates my socket. It has this method here that's part of Python, create server, and you would create a server depending if it's an IP6 socket or an IP4 socket. And then I want to set a timeout, and the timeout is very important because sockets will wait forever. We don't want our program hanging up, so we give it a nice reasonable timeout. If things don't happen fast enough, we just time out, and then we can reconnect. So once I have that socket, my server is ready to go. I will start my server. I use a Boolean when I'm doing a kind of a thread. So this is going to set up a thread. I use a Boolean to shut off my threads. There's no definitive shut off. You can wait for a thread to die in Python, but you don't just shut it off. So I use a Boolean because Booleans are atomic. So it doesn't matter what thread you're in. There's no state of a Boolean that is some kind of on and off, but not one or the other. It's always either on or off. So I can send messages between different threads pretty safely with a Boolean. So I have this Boolean that says, if it started, I'm just going to turn around. I'm going to return. I'm not going to let it start twice. And then I have this little run method. You can subclass threads, but I like to. This is an easy way to do it. I just create a little run method. I put all my code that I want to run inside my thread, and then I come down here. I just create a thread, and I use that run as a target in the thread, and then I just start the thread. So after it starts, it's going to take that socket that I created, my server socket, and it has this method called accept. And what accept does is it just waits. It waits for someone to send a message. That's why we have that timeout, because it'll wait forever. And it's just going to wait, and it's going to wait. And if it gets a message, it's going to be returned as a connection. And that connection, I'm also going to set another timeout because it's a different socket connection. It's not the same as the server. And then I'm going to go through a couple of things on that connection. The first thing I'm going to do is a handshake. Everybody knows what a handshake is, but in networking, your handshake is kind of when you're getting to know the person you're connecting to. Do they have the right name? Can they verify credentials? You know, I don't want to just take information from this person or send information to this person without knowing who they are. So that would happen in a handshake. If it passes the handshake, then we go and then we handle the request. And in the case of this server, the request is just going to call a function that we pass in from another device, from another piece of code. And of course, when we're all done with that, it's going to shut down my connection and then go back to the top of this loop. It's going to say, is it still started? Right. So now I'm going to go back and I'm going to listen for another connection. It's still started. I'm going to back. If I wanted to shut this down, I would set the Boolean of this started to false. So when it goes back to the top of the loop, it says, "Are we started?" And it'll say no. Then I'll just exit out of the thread. Real simple. If you don't do that, you could get in problems. So always, anytime you create a thread, think about how am I going to leave this thread safely. Okay. Here's my stop method. It just takes my start. It says it sets it to false, and then it closes the socket for good measure. That would be the server socket, because at that point, our server's done. We're not going to restart it. Here's a couple of methods that I want to override when a subclass is. I'm going to handle my handshake, and I want to handle the request. Now I've got that's our TCP server. Now I need to do a UDP server. How am I going to broadcast my IP address to some potential service? UDP servers are a little more tricky, as you see earlier, the trouble I had earlier. And the reason is that it's not as well traveled a part of the IP suite, but you can do them in Python. They're just a little trickier. So here, my UDP, I have an IP socket address. There's certain UDP addresses that are reserved. Forgot to write down what they were, but if you look in the documentation, there's certain IP addresses that are specifically reserved for doing multicast addresses, and that's what we want to do. An administrator might lock down the multicast address, or they might leave just one open or a handful open in a particular mask. And that's probably what is going on here, so that you can't just create them, because as we said, UDP broadcasts to everyone. Do you just want any device to simply say, hey, here I am, and then repeat itself over and over again? Probably not. So best to have that managed some way. To create my UDP server, I'm going to create what's called a socket for a datagram. And they've got some fairly, I don't know, they're kind of low level things that you have to pass into this. Here's a socket. This is going to create a socket in Python. This is the code that you use in Python to create socket. You have to pass in the name of the family, and you have to tell it that you're trying to create a datagram, and you want it to be a UDP port. So then you have TTL, time to live. You want this command to go out, and what's going to happen is you have networks. I think my counter will get clicked over here. You have a thing called TTL, time to live. In most networks, time to live just means that when it's going from server or from router to router, it de-increments, so you don't end up in an infinite loop of going from one router to the next. In UDP, it does not de-increment. What it means is that it will go up a certain number of routers. So if I have a TTL of 1, it'll only go to the one router that's on top of the local network. It won't get bounced to the next router up. This is a weird Python thing. Struct. Anyone use the struct library? What that does is it packages your integers into a big Indian or little Indian format. That's Indian END, which means that the big bytes go first or the little bytes go first. Networks generally like it to be with the big bytes going first. Java uses big bytes going first. A lot of applications do it the other way for networks, or do it the other way. So then I'm going to pass that in as a socket option. It says it's going to be create an IP6, create multicast hops. There's my TTL, and then so I would create a socket this way if it were IP6. I would create it this way if it were IP4. you usually have your choice of both. Most networks these days. It used to be that most networks only had IP4. A lot of protocols only use IP4, and there's actually a lot more tools for IP4. And as you go looking around for examples, most of the examples you'll see are for IP4. But you should be able to do everything today in IP6. Okay, so that creates my socket for my UDP server. Its thread starts a little differently. We still have this little start Boolean that I use, but I'm going to repeat it a little differently. I'm running it through an algorithm that's going to allow me to broadcast the message a certain number of times and then stop broadcasting that message. So I add one message that's going to broadcast for a minute, and I add another message that's going to broadcast forever, but only once a minute. I'm probably not going to cover that as just too much time. Again, there's my thread. I pass my run message in. This is actually important. Daemon threads. Anyone know what a daemon thread is? So a daemon thread is a thread that will die when you close your program. If you don't specifically make it a daemon thread, it could try to stay alive and keep your program from closing. That's actually useful if you're saving something. You want to make sure it's properly saved before your application closes. If it's a daemon thread, your application is going to close. It doesn't matter. In this case, I just want it to be a daemon thread because it's not going to be able to do anything. And I don't want hanging up anything. So I make these threads daemon threads. Now here's my UDP client. Again, I've got my socket address passed in. I'm going to create my client socket based upon its IP address family, IP4, IP6. I'm setting those options here. We had to use struct to pack those again. And I'm setting my timeout to 20 seconds because I really don't want to listen for longer than 20 seconds for a message. Again, here again, I got doing my thread at the run. This time with my socket, I use the method in Python called receive from, and I put in a packet length. When you are receiving your socket, it could be of any length up to, well, there's a limit, but you don't know how many bytes are going to be read. You could say, okay, I want to read 100 bytes at a time, but your message may only be 50 bytes. You're going to read 100 bytes, whether it's 50 bytes or not. So having a packet length that's reasonable for the messages you're sending is important. I just picked around 512. That's about the size of the buffer. And then I've got a function that I've passed in earlier that's just going to be listening. So if I actually receive something, again, this is going to be waiting here for the receiving. It's going to wait for 20 seconds. If it doesn't get anything, what's going to happen? It's going to run back around to the top of the loop, and it's going to check to see if it started. If it's still started, then it's just going to create another. It's going to listen to the socket again for another 20 seconds, and that way I can always get out of this. When I hit stop, I know that within 20 seconds that loop's going to exit. Okay, if you noticed, I didn't have a TCP client. TCP is actually really easy to do. So I just put that here. When I connect with the TCP address, I create my socket with my family. This socket stream here just means it's going to be IP4. or I mean, it's going to be a TCP socket. All right. Now that I have all my servers built, I'm going to do a device. How do I create a device? First thing I want to do is I want to have an IoT device server, and I'm just going to extend the server that I've already got. That makes it easy, and I'm just going to override my methods. Handle my handshake and handle my request. My handshake is pretty simple for this one because it was just a demonstration. I'm going to look for a request that has the word that starts with the word handshake, and then I'm going to get a host ID, and I'm going to send back a response okay. So that way the client knows that it's properly handshake. What I could do is for security, I could send a hash code that would be a hash of some message that both the server and the client would know that some secret key that's been hashed. That's an easy way to do it. You could, of course, use key encryption and all sorts of things, but in this case, we're just doing a handshake and saying, okay, I've got the handshake. I've got the host ID. Verifying that the host ID is the right host. Then you would handle the request. And in this case, the request, I've got I have some function that's going to be listening for the request. And then I'm going to write a message. I also have a little function in here to publish my device, and this function here is just going to create my UDP server. It's going to create a message. Here's some device ID, the name of my group, what my host name is down here, what my port is, and that's going to be my message. That's going to be my UDP message. Then over here, I have to monitor for requests. How are we on time right now? Okay. I'm going to kind of jump to the program. So I've got my sensor program here. Commented out. I've got this commented out because on this computer, it's not supposed to be running on this computer. I didn't want it to go through it by accident. But there's a transition counter that I talked about earlier, and it's going to handle I got a little definition for handling a request, and I'm going to pass that in. Create my IoT device, called sensor and host name, and then I'm going to start my device, and then I'm going to publish it, and that means I'm going to send out to the UDP, and then I'm going to run a little loop until it exits, and then when it exits, it stops, and the whole program ends. So once you have all the tools, all the servers and all the sensors, it's a pretty straightforward process to actually just create a device, give it a host and a port, and handle requests. Here's my request handler. You look at that, it has just a couple little requests. One is a count. They can request a count, in which case the response is given down here. it sends the counters count, right? The other request that it can get is a reset. So if my numbers are off, I just want to reset it. I can hit the reset button, and then the response there is just an OK. So my client knows what the request should be, and it knows what the responses should be, and my server can handle those. Now on the people counter side, again, it's a pretty straightforward application. This part up here actually creates a display. It uses Tkinter. Anybody use Tkinter in Python? So that's the windowing tool in Python. It's okay. It's good. You know, it's not React, but it's pretty good. So when the say the client, the service starts up, the big counter, you know, some counter on the wall, and you can have several of these. When it starts up, it's going to bind its sensor by sending in either a host and a port, or if it doesn't send a host, it's gonna go and try to. If it sends a host, it can create an IoT connection directly. If it doesn't send a host, then it's going to turn on its monitor, and it's going to go to turn on its UDP monitor, and it's going to wait for something to send a host IP address and a port number. If it has that, it can do this directly. If it doesn't, it has to wait. And then this is what happens if a host is acquired, and this is actually my function here. The monitor acquires a host. It's going to send it a reference to this function here, which is going to be where it's going to update the connection. And then it's let's see. Which, oh, winding down. Okay. Yeah, so inside its run thread, it's going to submit a request. There's either it's going to reset or it's going to submit a count. The request is going to come in as data, and this data is depending on how you do it. I did it as a string in this example, but you can parse that string into JSON. So I did that. So I can send my data as a dictionary, a Python dictionary, and it gets put in as a string. And the results I can then just read out as my response to the count would be a number. Response to the reset would be an OK. And then it just does that over and over again as long as the counter is running. And that's that whole program there. So, you know, you have your IoT or your TCP server, you have your UDP server, you have a TCP client, and you have a UDP client, and then your application basically creates a connection between the two. So the whole application here for the counter is you know 164 lines, mostly white space. So once you actually have your server developed or you're using a server, it's pretty easy to actually connect. I wish I had more time, but I wish I could get in, you know, better in this. But has anybody followed any of this? Is this useful in any way? Okay. I think I'm gonna have to wrap it up and do questions. I don't know if you can see this. So we put lights up here so you know what it's doing. The lights don't necessarily have to be there. The person walks this way, walks that way, see that the lights change. Person walks this way. that way, and then it resets. Oops. I don't know what's off. Anyway, so what happens there is this sensor is picking up and that sensor is picking up. And what was supposed to happen, you'd be looking at a big screen with a bunch of numbers on it changing. That was the plan. So imagine that. Okay. All right. Well, that's about it. Yeah. So any questions, anything on IoT, anything on a Raspberry Pi that you wanted me to cover and I didn't? You know, like how you set up a Raspberry Pi. Didn't get into that at all. Yeah.
That still would be the same as.
So an HTTP request, HTTP is a protocol that uses TCP/IP underneath it. It kind of wraps around it, and it basically sends text. It's a protocol for sending text, and that text is then encoded and decoded. So if you're using that, you need to have an HTTP server, which is usually a bigger deal. HTTP server is a really big library of things that it can do. So yeah, it would be different, much more intensive to have an HTTP server running on your Raspberry Pi just to turn on some lights. This is very minimal. All of the socket code is actually part of Raspberry Pi's standard library. So you don't even have to import it. It is a little bit difficult to get going in some Raspberry Pis because you have to have permission. You usually need to have root user permission. Right. Anybody else? I'm missing somebody? Yeah.
Is there a benefit to using a Raspberry Pi over converting this to Arduino?
Okay, that's a good question. Raspberry Pi is it's like having the really big box of crayons in kindergarten, right? Arduino's like having that little box of 8 or 16 colors. You know, you just don't have, if you've got the code and it works and it's simple code like this, yeah, this could run on Arduino. There's no problem. I would have to use MicroPi, and that might not have some of the libraries in it that you need, depending on what you're writing. Or you could use Arduino's language, or I guess C in some cases.
That was my experience, because like in this specific use case, it seems like not a lot is being factored.
Okay, so as far as your device, the service is agnostic. It doesn't care what your device is. It's using TCP/IP and UDP. As long as yours can send the right string to it that it can decode and that it can send back, it doesn't care. But the Raspberry Pi is really great for prototyping because you'll find it has every tool, right? If you don't have it in Raspberry Pi, then you're doing something that you really shouldn't be calling an IoT device, right? But yeah, even you know, the Zero or even the Pico would probably run this. Like I say, it depends on whether or not you've got the right libraries in your socket module.
Thanks. So the reason I asked about the
Okay, so JavaScript, right? JavaScript kind of operates in its sandbox, so it really likes to talk to HTTP server, but you can also use something called WebSockets, WebSockets is a protocol that sounds like a socket, but it's not a socket. It's just a protocol that talks to another kind of server that serves just a way that a WebSocket likes. I've written servers like that work with WebSockets. They're not that complicated. So you can actually write a WebSocket server. Use just the same way you'd start out by writing a TCP server, and then you just handle the WebSocket bytes as they come in a little differently. Yeah, and that would allow you to use JavaScript. Say, I'm not sure how you do this, like using fetch. Like say all those, they basically want to use HTTP.
If somebody wanted to start messing with Raspberry Pi first time, where's the best place to point them? Starting a journey here.
Yeah, yeah, Raspberry Pi. Yeah, Raspberry. their website. Their website. Raspberry Pi. I'll get a little history on Raspberry Pi. Is started by some engineers that worked for Broadcom. And they basically said, hey, we've got this chip here. We can do a lot with it. I bet we can run Linux. And it's kind of, can we run Linux? And they built this thing that could run Linux on this little tiny chip. And they put it out as open source. And of course, it kind of blew up. Everybody kind of wanted to be able to run Linux on a little cheap thing. And they made a very conscious decision that this would be a $35 computer. And it actually still is a $35 computer. But if you want a little more RAM to run things, I can run Eclipse on my Raspberry Pi, which is actually a big program. But if you only have 1 gig of RAM, which is what the $35, you're not going to be able to do, so you can pay a little bit more for that. But Raspberry Pi is cheap. So the benefit of having Raspberry Pi is especially if you're learning Linux, you can make all sorts of mistakes and then just reflash the drive. And the drive is just an SD chip. So the way you get started is you get a Raspberry Pi, you get an SD chip. I recommend kit or something like that. There's a couple different kits and they're around $100. They'll come with everything else that you need that you don't get in your Pi, like your power supply doesn't come with your Raspberry Pi. A keyboard, doesn't come with your Raspberry Pi, but any keyboard will do pretty much. They sell a nice neat little Raspberry Pi keyboard, kind of expensive, not really anything special, just $10 keyboard. It's all you need. Raspberry Pi Model 4 does need a very special HDMI. It needs the form factor of the micro HDMI form factor. So you got to buy that separate. Sometimes you buy the kit, it'll have everything in it. Everything to just open up the box and start using it. The program that launches the whole thing is called Noobs, new out-of-the-box software. And what you do is you could use the one that comes with it, but it's usually out of date. Just go to the Raspberry Pi. There's a program at Raspberry Pi that creates that. It flashes it onto a little chip for you. You can select which operating system you want, which flavor of. You could use Ubuntu if you want to practice your network skills. The standard one is called Raspbian, and Raspbian is it's a fork of Debian, it's built on Debian, which is very solid. That's by default, and it's what they've done is they've taken everything out of there that would interfere and make it too big or too bloated. So it runs best on Raspbian. But you can launch it under different configurations. If you want, I could. I can't disconnect. I could disconnect this and plug that in, and you can see the desktop. it looks like a Windows kind of desktop now. It used to be very Linux-like, where you had to type in a lot of commands and learn a lot of commands to get it to do anything and have to install things. Now it just boots up that you just says, ask you for a username and password, you know, and it just launches right into it. Very easy to install. As far as Python, Python is built into it. There's a couple little IDEs that are also built into it. Phony is one, and Genie is another. And they're built into it. It also has support for VS Code. So, thank you.
For the ones that are